Okay, excellent.
Okay, so now let me share screen. Let me start presentation. Okay, so welcome everybody. So let's start. So first of all, a little bit about me. So like I totally forget to ask. So what are you doing?
My profession?
Yes,
I'm data analyst.
data analyst. So where do you work?
Dental software company.
Okay, good. So what is your name?
My name is
Okay, good. So now, like I know everybody. So my name is Yuri Panchul. I work as sortier design engineer. So right now I work at Samsung, and before I was working in Juniper, which is doing part of core router chip. And before that, I was working in MIPS, which is a CPU company. Making embedded processors, and I was also a founder of EDA startup in the area of electronic design automation. So this startup was funded by Intel Capital back in 1999, and some other VC before that, and in 2001 was sold to Synopsys. And more than 10 years ago, I started to be involved in different educational programs, because I was working in a company called MIPS, and MIPS was doing some business in Russia. So they asked me to help them in that business. And then I went to educational side of it, so started to do classes in Russia, Ukraine, Kazakhstan, Kyrgyzia, then Armenia, Azerbaijan. So most recently Azerbaijan, and I'm also a co-author of a package called MIPS FPGA, which is educational a package which was used in many schools around the world, including University College London, and schools in Japan, in China, in Europe, and here in the US. So when I was doing MIPS FPGA training in Russia in 2015, in both Russia and Ukraine, I noticed that students actually need many students need some more elementary introduction, and this is how such elementary introduction was born. So this is one thing. So later on, when I was interviewing interns and engineers in different companies, I found that there is a gap between school and what industry wants. And so can we talk about this gap a little bit? So I also started to create example which help students to prepare for their future in the industry. By the way, if somebody doesn't speak English, I can repeat certain like certain things in Russian, or you can speak Ukrainian in it because I know both languages. So, like, is it okay for like everybody if I speak English? Okay, 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 okay. This is fine. Okay, now. So, like I said, that we have mixed audience. So for like people who are like already familiar with a Verilog, this concept of RTL to GDS flow. So we have at least like two gentlemen from Samsung and from Intel who like already know this. So like if they're bored, they can like work on my questions. I usually give to like students and just tell me what they think about it. And for like everybody else, I will give some like talk about what we are doing. So first of all, today, what I found from my experience, that people need to be like immediately occupied with playing with FPGA boards. So like if they don't play FPGA boards, they get bored of lecture and just leave after 1 hour. So that's why I brought FPGA boards and you can play with them. Now, if you have a computer, I also have many bootable SSD drives. So you can Linux with those set up on your computer and play with these boards. They will show you what you need to do. Just a second to find my SSD. Yeah. So here is the bootable SSD with Linux, which has everything installed. So like if you have a computer, what you do, you simply get this SSD and you boot from this SSD and you go to the complete environment. So does anybody want this bootable SSD? I'm not sure whether it boots on Mac.
Okay.
Huh?
Do you require Linux to like run this whole thing?
No, you can not the whole thing. So you can run it either under Linux or under Windows. Or some things you can run on Mac. Particularly, you can run simulation on Mac, and you can run open source tools on Mac. Yeah, so there is a set of open source tools called Yosis-based toolchain, which runs on Mac. Just I can show how to do this. So in principle, we can replicate all this environment on Mac if you want, and I can show how to do this. Just I personally didn't do this on Mac. Like I do have Mac, but I did on Mac only simulation. So if do you have Brew on Mac? If you install a tool called Icarus Verilog, you can do a simulation on Mac. So Icarus Verilog. Okay. So you can as well, and you can actually try some of this exercise. So does anybody want boot? Huh? Yes, you can. Thank you. Okay. Okay. So does anybody want bootable SSD? I have. I will give it. Just a moment.
So are all of these SSDs loaded up already?
Yes, they're all with Linux. So I'm not sure whether you can start it on Mac. If this is ARM-based Mac, you probably cannot. But if this is x86, you probably can.
One of the Intel, which I believe is based on.
Okay, so let me first give a hub with USB-C because they do have such hub. And then like, you can just get board, assemble, and follow this exercise.
And so, do you require Linux to run this like or can you VS Code this when you run?
Oh, you can run it under VS Code. You just go to VS Code and run scripts. Yeah. So there is nothing really. Okay, just a second. I will give you the hub. Yeah. I do have tabs specifically for people who have only, yeah, this one. Okay, now so let's continue. So, and I have multiple FPGA boards, but right now I want to switch many students to use of Go and FPGA boards because they simply have they simply have faster synthesis and they're cheap. So it's possible to just and I have this like setup with this board. But before we go to this stage, I want to give a little bit of like general talk. So basically, once you go to either terminal or VS Code, you just run this three commands. So you're going to directly the lab, and then you just run one script. So this is essentially one push button activity. Now, so first of all, let me tell you the main idea of modern hardware design. The main idea of modern hardware design was born. Just don't let me, for better sound, just connect my microphone. So people invented digital design approximately in 1940s. So people were doing some switches even before 1940s, but they were using like electromechanical relays, and then like invented vacuum tubes, and they were doing switch designs, and then they like invented gates and flip-flops, which is the like elementary 1-bit unit of storage. Then when people invented microchips in like 60s, they first were designing them just using some colored cardboard or drawing with a pencil. And in fact, I met the guy who designed the very first microprocessor, which is Intel 4004. And his name is Federico Fagin, and he was actually one of investors into my startup. So he like invested his own $50,000 into my startup back in year of 2000. So like I met him, such people who did the very first processors, they still like live with us. So, and those people, as well as designers of like Z80 and all processors of that time, they were just using pieces of cardboard and a pencil. And then like during 80s, some people started to use computer stations to design, and they were like drawing schematics with a mouse. But then in 1988, the modern technology was invented, which we still use today, so like 35 years ago. And this technology is called RTL to GDS2 flow. So like in Russian, it's called the Marshрут RTL GDS2. What? 1 second. So if somebody on Zoom can hear me, yeah. So can you hear me? So okay. Anyway, so basically, what is so there are like several terms, and let me just briefly tell them. I will explain what they mean later. So one term is hardware description language. It's language which describes hardware. And register transfer level, I will explain later. So ASIC, application-specific integrated circuits. Practically, right now, everything you see is ASIC. Like microcontroller is ASIC, chip inside phone is ASIC. But back in like early 80s, there were like custom CPUs, ASICs, and like other components, so it was a little bit different. But right now, the ASIC is pretty much every chip which is manufactured on a silicon foundry. Yeah. Now, system on chip, this just means ASIC, which has a CPU core in it. So as simple as that. And a field programmable gate array. So many of you are familiar what a field programmable gate array is. So I mean, like two gentlemen know, but okay, I will explain this to the rest. So now, like practically everything you see, like in like smartphones, like AI accelerators and so on, designed using this methodology. So like TPU, like fast internet, and so on. So now let me go to the point. So suppose you have some chip like a microcontroller. Like suppose you have chip like inside Arduino or something, or you have chip in a computer or something else. So here we have a dualism. So you have a CPU, and CPU hardware of CPU is designed in Verilog using this methodology we are going to talk about. So you write code in Verilog, and this code becomes like transistors and connections. And this has memory, and memory stores your program as a sequence of instructions. So basically, every program in like C or like Java is a bit more complicated because Java has in-time compilation, but eventually all programs is just a chain of instructions. So and the CPU, yeah, and there are some peripheral device controllers, and they are also designed using hardware description languages. So what's the difference between software language like C and Java and hardware description languages? So when you have software, you write like program in C, right? And compiler converts this program into a series of machine code instructions, right? So you use like assembly language as intermediate representation, but assembly language pretty much maps directly to this chain of instructions. Okay. Now, hardware is different. So with the hardware, when you write some code, this code first is converted into a structure, into some like graph of logical elements, of logical and memory elements. And then there are programs called place and route, which just place this graph on the chip, and eventually you are getting a file in a format called GDS2, which describes chip in terms of geometrical figures. So like it's saying that this is like silicon, but let's put here like copper wire, and let's put here some like silicon together with phosphorus or like something else. And this just has rectangles inside. And this format GDS2 was invented very long time ago, back in 60s. But it is still used. So this is very like conservative format. So during that time, chips were like 10,000 nanometers, so like 10 micron, and now it's 2 nanometers, so we shrink like 5,000 times. But but all like electronic companies still use GDS2 format. So now, what is the main idea of digital? This is something like a few people understand immediately, but I will like say it. If you don't get it, don't worry, we'll talk later. So basically, all digital logic, like everything what you have, like CPUs, like graphical processor, can be represented as a combinational cloud and state registers. So combinational cloud is essentially a bunch of and or not kind of elements. And combinational logic just means that this logic has no side effect. You just put something on input, like you put on input A, B, C, D, and you wait for some time, and after some time you get answer. So what this formula? So this is just a formula. This same input always gives you the same output. The only thing is that in hardware, because of physics, signal is not propagated immediately. So there is like some picosecond delay here, picosecond delay here, and so on. So now the question is that when can you get the result? Number one question. And second question, how can you make circuit to do something interesting? Not just be like table of for a function, to like repeat actions and so on. So in order for so this is slides. Not everything happened immediately. Now, what happened is that we use a special signal called clock. It just goes up and down with a certain frequency. So when you go to store and you buy a computer which has like 2 gigahertz clock, this just means that the like main clock works with this frequency, but in reality, usually such complicated system on chips like have many clocks with different frequencies. But usually one like large block, like embedded processor core or GPU runs on one clock. So when you have like multi-core, you may have like manager of those cores run with different clock, but it doesn't matter. So for a simplicity, as now we have one global clock. So now, once you get those two elements, which is the combinational logic and primitive bits of memory called D flip-flops, like in Russian, it's a dead trigger, you can implement everything. Because you can implement like state machine, pipeline, so any like imaginable algorithm can be implemented using those elements. One element is logic gate, and another is one bit of memory in D flip-flop. So, and here is the animation of a simple sequential circuit. And once you meditate with this animation for some time, you will understand everything. Because any complicated chip, if it accepts like multiple clocks and domain crossing, can be reduced to group of combinational logic element and state element. So now what happened is that here we store state, and it is kept constant for a clock cycle. And then we use combinational logic to compute new state for the next clock cycle. And such steps you can compute any given algorithm. Now you would ask, why don't like Microsoft in this case put all Windows in hardware? So just like you don't have software at all, and everything just runs in hardware. The reason it is not done, it's because you will get chip of size of this room. This will be not very much economical. So, so for like economical reason, it's better to have CPU and software running on this CPU. But in principle, you can implement everything in hardware. And when you one example is like networking chips. With networking chips, if you implement networking core routers in software, they would become 100 times slower. But the hardware handles the most frequent case of like handling packets and gives to software only some like unusual cases. Yeah, same thing in GPU. So like we like at Samsung GPU team process a bunch of like colored triangles and convert into scene in a computer game. using rasterization. To do this in hardware, if you do everything in software, then each frame will be drawn very slowly. So like 2 orders of magnitude slower. Okay, now, so now, yeah, so this is like all basic theory, because if I tell you more, you will probably get like overloaded. Now, so once you create design, so what you do with this design, so you send it to Silicon Foundry as this GDS2 file. So you just so companies were putting files on FTP, and just on Foundries they create a set of masks. So like in Russian it's called photo shablon, and then they mass produce chips. So there are multiple options for manufacturing. So when we do mass chips for like phones or for some other like expensive devices, the set of masks may cost like tens of $millions. This is like initial price, and this is the reason why we don't produce chip for like any given application, because of this like initial cost, which should be spread to a large number of units. So now, but what do you do if you are a university researcher and you want to create your own chip? So there is a service in Europe called Europractice, and in US, Moses, and with this service, you can usually like Silicon Foundry, like a factory which makes chip, they have some like extra capacity, so they can produce some like extra chips for researchers, and they just let them use to produce just a few chips for them. And if you are willing to do chip not like 3 nanometer but like 130, you can do it for just a few $1,000s. So now, how to make, but this is too much expensive. So recently Google actually created a program with a company called Skywater. So Skywater is a only completely US owned foundry like in the US. So this was used like mostly by like military people who don't want to like depend on like Asian foundry, but now they partner with Google, and they let people to upload design, and if Google like your design, they can manufacture it for free. Or if they don't like design, you can pay like $6,000 or $10,000. They manufacture your chip. But now there is a new thing called tiny tape out. Like it's handled by a person. His name is Van, and I just chat with him recently. So what they do is that they let just people like all of us who usually cannot afford to spend like many $1,000s to make just one chip, they like allow to spend just $150, and they get one chip for like $10,000, split it into pieces, and let each like hobbyist to actually create a little design for only one piece. So, but still, you need to create some simple design, and you need to wait several months until you get your own chip. So, what do you do in the meantime? And same thing as like we at Samsung. We at Samsung cannot, after each design change, to send design to the fab and get back a chip, because we are doing like every day, many engineers do like a lot of changes, and we can send to the foundry like only like a couple of times a year. So we need to make sure that what we send like really is robust. Okay, so for this reason, first we use simulations, and then we are using so-called emulator, which uses FPGAs. So now let's talk about FPGAs. Yeah, but before we talk about FPGAs, So how chip design team works. So basically, chip design organization which design chips in different companies looks surprisingly similar. So like if you get like Juniper, Samsung, like Apple, Nvidia, like Intel, AMD, they have like similar type of organization, and this is how like it looks like. So first of all, there are like two dimensional structure. So first you have divisions. So you have a division which do like architecture, RTL design, design verification, and they which do like physical design and silicon debugs, like software stacks. But also chip is divided into blocks. And for each block, there is team which consists of several members of this different department. Okay. So now, yeah, so one role is the role of a block microarchitect. So like it's a person like me, and basically the responsibility is that we get requirements. So this all starts in like technical marketing. So technical marketing people like they collect some data how new chip should like look like. For example, like technical marketing can say, oh, for this year we need to like introduce some additional like AI accelerator because software people found how to use it to like improve quality of like some like handling graphics, recognition, sound, and so on. Or for this year we need, in order to be competitive, like increase number of cores and how much and so on, or like make like a higher frequency. So they like collect a technical marketing, and then a group of chip architects create a high level architecture and give architectural specifications to people like me. And this architectural specification is telling what block should do. Like block should accept some pieces of networking packets and cut header and replace with another header. Or block should get coordinates of triangles in 3D space and like convert them to put your like scene in your like computer game in some like perspective. Okay, so now so a person like me, microarchitect, sits down and write a document called microarchitecture specification, which has a bunch of diagrams like this, which shows how data are moving inside the block. And once once we have some meetings where we review this with architects and like other involved people, because we also have some requirements from like a physical design for like timing, budget, and so on. This is implemented in a Verilog hardware description language. Yeah, so this looks like this. So like writing code with the blocks which have like inputs, outputs, which have like state element and combinational logic. And basically RTR design engineer needs to work with the verification engineers that check that this block is implemented right. Okay, and and then like so what is the process of verification? I don't want to talk too much about this because I don't want you to like swamp with the details, but basically how like it happened when we have block functional specification. So because humans make errors, and correcting errors once chip goes to foundry is very expensive. So chip respin is $20 million thing. So if you made bug, it went to fab. But this is not only that. It's much worse. So basically, here is the life of a chip project. So basically, this is the time. So you are doing like chip design suppose for 2 years. And that you are doing chip design for 2 years, you start selling it. And initially you sell a lot and then you sell less and less, right? And suppose that you can sell it for 3 years and after this chip becomes obsolete. So basically this phone is like very like clear example. So each year all phone manufacturers make a new phone on Las Vegas exhibition, and like companies compete with each other. So Qualcomm, Samsung, and so on. So now now the problem is if you sleep, if you discover bug too late in the design cycle, then which means that you need to respin and then you can go to the market later. If you go to the market later, your competitor comes first and eat all this piece of money instead of you. So basically, if you come here, you will get much less money. So it is very important to find such bugs very early. And this is the reason of such complicated structure of verification to exist. And this is important because there are many jobs of verification, like even more jobs like than in design. Many people who do programming can actually, once they understand basics of digital logic, they can switch to verification field. So what happened with the verification? When you have a block specification from architect, it goes to 3 persons. One person is a modeling engineer. Modeling engineer is a software programmer. He writes program in C++, which creates mother of this block in C++, using transaction level. So he doesn't know about clocks. He just writes a flow of transaction. Like we get piece of Ethernet packet, and we like send it to the connection. So this access C++ class object. We like analyze what is inside, and then we send outside like something else. So this is a software model. And the modeling engineer works independently from a block architect, like a micro architect, RTR engineer, who implements in Verilog what a block actually does on clock level. And because there are 2 minds separate, both me and this another person who is a modeling engineer interpret this specification in a different way. So we basically read it and we can read different things. We can understand it in different way. But then design verification engineer, he also reads the spec and he also interprets it his way. And he create, okay, now I need to create a test plan. So he's a judge who compares work of mother against the work of RTL code. So he created a bunch of tests, and he runs this test, and he sends the same data to mother and to the block implemented in Verilog, and then compares response. Okay, so this is called like reconvergence of interpretation. So this basically uses fact that if it's not likely that many people make the same mistake, so they will probably sort of check each other. Now the question is, suppose design verification engineer is lazy and didn't write enough tests. So he's all tests pass, but actually there is some hidden bug. In this case, we need fourth engineer who is verification engineer with a specialization on functional coverage. And he uses special language to check that every item in test plan is actually covered by the tests. So this is like beyond the scope of today of discussion, but there is the whole world of this thing. So now, yeah, so now what happened is that we run on simulator, and you can actually put Icarus Verilog simulator in Mac as well as Windows and Linux. So what is the difference between free simulator and the industrial tool? So we are using like Synopsys VCS and Verdi and Cadence simulator and SimVision. They are like expensive tools, but we are using for this class only like free tools. Their main differences of capacity and speed. So Icarus Verilog runs like 60 times slower than commercial tool. So, but this is enough for the current purpose. Now, in addition to engineers who design logic, there is the physical design engineer. So people like me design logic on the chip. So write some of combinational logic, state elements, but a physical design engineer, he needs to verify that whatever logic we create here actually like fits timing budget. Like if we put too much logic within one clock cycle, so suppose that in one clock cycle we need to compute multiple things. So suppose we need to like to put too many this like and or, so we have long combinational paths. And suppose all this delay may take like 2000 picosecond, or like this is like two nanosecond. This means that you cannot run with the clock speed of 1 gigahertz, because 1 gigahertz means that you need to put only up to 1 nanosecond in a clock cycle. So physical design engineer, he is like concerned about timing and about placing all this logic block on the chip, and he is using some like also very expensive tool to take care about such physical problem. He is also concerned is like power consumption, so place and route, power consumption, timing, and later on like signal integrity, that you don't have some physical problems. And person like me also works together with a physical design engineer who provides a physical floor plan, which is a like large scale plan of what is on your chip. And then we put our logic into this floor plan. He checks that we fit into clock frequency budget. Yeah, so this is like a main team. Okay, so like any questions about this? So basically, electronic company, like any company, so like Samsung, Qualcomm, NVIDIA, and so on, consist of such divisions and such groups around each block. Now, what is FPGA? FPGA were invented in 1985 by a company called Xilinx. And FPGA, they actually surprise people a lot. So we are with FPGA today, because this chip which doesn't have a CPU. I mean, some FPGAs do have CPU on the side, but this is like additional CPU, but FPGA can be made into CPU. So now the question is, how can you change logic inside already made chip? This is done using a trick. And this trick is that we can implement any logical operation like AND or XOR not by such a universal gate where we put like numbers A, B, C, D into memory. And depending on those numbers, the whole structure behaves S is a AND or XOR or like any other like a binary function of X1 and X0. So this thing is called a multiplexer. A multiplexer is like hardware if. So basically, if you put here 1, then it will choose D, and if you put here 0, it will choose C. And by putting those 3 multiplexers and by putting different numbers here, you can put either like AND or something else. So I can actually explain this in more details later, but now you can just like trust me that you can implement different hardware functions in such structure. So now your question is, if you can easily change hardware in FPGA, why don't you have FPGA in like any computer, telephone, and so on? And actually, in like late 80s, some company here in LA, actually very close to us, the company was the virtual computer, and I visited them in 1997. So there were like a couple of people there, and they were mostly working with like militaries, with special services and so on, because they special services use FPGA to like break decipher something, so to break codes. And also used for like DSP, for digital signal processing. But while doing such contracts, those people also aimed to make a configurable computer on every desk. So they were saying that we will make a computer which can change its hardware. It will be like a revolution, like a personal computer. But this happened, of course, because FPGAs, they have very high additional cost. So if you implement, suppose, OR element in ASIC logic, you need just a few transistors. But if you implement OR element in FPGA cells, this lookup table, you need 10 times more transistors. So basically, if you get like Intel processor, and if you put it into a bunch of FPGAs, and this is what Intel actually does when they debug processor, you will have a box called emulator. They actually have this box in a different presentation, but doesn't matter. And you have same boxes in Samsung and like any other like electronic company, but a processor implemented in such box will run with only speed, like on a frequency of like 20 megahertz instead of like gigahertz. So it's still good enough to debug like starting Linux, but this is not nearly competitive with like fixed chips. But this is still great for us in doing such exercise. And the FPGAs are also used for like special applications, like if you especially many like young people can go to get jobs in like aerospace company, like Blue Origin Aerospace. They actually advertise jobs for FPGAs, because what they do is that they cannot make ASIC for every single rocket, because number of rockets is small. And when you do ASIC, you need to spend a lot of money. So they get a bunch of FPGAs and microcontrollers and create network of FPGAs and microcontrollers, and just use those FPGAs to work with like sensors, like control like fins and so on. And so and for FPGAs there are also open source tools. This is person named Ruslan. So he actually lives in Siberia, in Tübingen. He's enthusiast of of open source FPGA tools, and he created his board, and that script which can run on Mac, actually he created it. So, but I didn't try it myself, so we are using now commercial tools. But if you want to try open source tools, you can look tools from like site I can show you and try. Okay, so now we are going to like another part of like our session, and this part is that how to prepare for like interview in like electronic company, and like generally what do you need to study to get into such jobs, in design, like is a mass produced chips or for like this one for like special application, like in like space applications. So first, because there any questions like so far? So you can actually start learning this like even while you are still in high school, because if you get like this book, and yesterday I met with the author, this book does not assume any background. So basically it starts from the beginning. It starts by explaining like binary numbers and the levels of voltage, like 0 and 1, and then you go slowly through all the like logic design, and then you go to Verilog, and then VHDL, and then you build your own little processor. And yeah, so you can yeah, so here's one of authors. So this is David Harris and Sarah Harris. So they met with David Harris yesterday. He is a professor in Harvey Mudd. So Harvey Mudd college is remarkable that it's not as big name as, let's say, like a Caltech or like UCLA or something, but they are very practically oriented. So, and they are in top colleges for the salary of their graduates. So they're like engineering graduates have like a high salary. So his approach is that in that college they do like every student to go through 3 different engineering fields. So they want a person to be both like a little bit of mechanical engineering, little bit of electrical engineering, little bit of that, and his belief is that by using such multi-directional approach, he can grow like a better engineer. And this book is effectively a collection of 5 different subjects. So one subject is digital logic, and another subject is Verilog and VHDL hardware description language, and then computer architecture using RISC-V architecture, and then microarchitecture. It's like what I'm doing, implementing in Verilog, and then using of like ready-made chips. So now, once, yeah, but his like textbook is actually used in many places, and such classes exist everywhere. So in UCLA, in the University of Southern California, so in like in the UC San Diego, UC Santa Barbara, UC Riverside, UC Bernardino. So everywhere here you have such classes, and some of them use this book, and some of them use other book. Like there is a book of like Patterson Hennessy, which was traditionally book number 1. So this book came later, but Patterson Hennessy covers less material. So then, once you master some basics, this is textbook which is used in Stanford and MIT, which goes little bit more into micro architecture, but not more to the level of industry. Because if person studied only this book, I can give him task or interview, he fails, and which we use all the time. I will explain you what it is. This is some textbook which came only couple years ago, and this is book with David Greaves. So one thing is that many like companies. So if you go to like Samsung, Apple, to the other companies, they used so-called credit-based flow control, like credit counters and stuff. But this is not described in textbooks up until now. So this is book which describes this, and usually people in companies know that students don't know it, so they don't ask it during interview. But if student can show that he does know it, he will immediately score kind of additional points, because this is like widely used. But this book doesn't have coding examples. So actually, one of purpose of like our open source like a movement around like Verilog examples is to create coding examples for such concept. And this is what we are doing in like Verilog Meetup, in Mountain View, and like over in different places. Yeah, then there is a good book on Verilog by Donald Thomas. The good thing about this book is it also explains mechanics of Verilog simulator. So one question I ask many students during job interviews is, can you give me example of a race condition in Verilog? So this like I will not explain what the race condition means, because I will bore you. But like in order to figure this out, you need to understand how Verilog simulator works inside. And this book has a appendix which actually explains it. So now there are books for verification. This is like art of verification of checking design versus model. And there are many like software engineers who started as a software people, but once they learn some basics of hardware logic, they can go to work as a verification engineer, and they can write like test environment models and so on. And jobs in like verification is the whole like its own world. Yeah, then there are some like special topics on formal verification, but we don't ask interns. And actually, we do. So when I see a resume of intern who is putting there that he is familiar with formal verification of assertions, I think that if interns wrote it, I immediately ask him to write assertion for like valid should be kept high until it's ready. So like this is like the most basic thing you can write. So this is like a hello like C program, you know. And many people who put this into resume cannot write it. So, but I don't like judge them hard, because I know that many students just like put it there thinking that nobody will ask this, but sometimes people ask this, like me. Yeah, so there is a guy, Cliff Cummings. So he is selling courses to electronic companies. So once like electronic company wants to train a group of engineers on some new methodology, like in system Verilog or like UVM, they can hire Cliff Cummings or like any of training companies like Doulos, like Willamette, HDL, but those classes are very expensive. So we are talking about like thousands of dollars per person per week. So basically, they essentially train in new methodologies to like improve skills, and they close some like deficiency of education system. For instance, like many students going to like very good schools, they cannot like describe like log domain crossing and so on, but company thinks that let's just get Cliff Cummings, put our young engineers in one room and let to train them and spend like 20 or $30,000 and just which improves proficiency of our engineers. So yeah, but he's like so he has a bunch of articles, and I highly recommend reading his articles for anybody who prepare for interview in hardware design or verification, because he like address things people frequently ask. But from another side, because everybody knows that people use his article in CDC to prepare for a job interview. Now nobody asks about CDC, because actually if you sit with his article for a weekend and just carefully study it, you will know how it works. So there is no point to ask. Now here, like I'm actually talking about experience with interviewing interns and recent college graduates. So this is there is some gap between academia and industry, and like 15 years ago, I thought that this gap mostly occur in like countries of former Soviet Union or like other countries. What happened in Soviet Union is that, as you remember from my speech, the key technologies for all this chip design business, they all were invented in late 80s. So basically, FPGA was invented in 1985, and logic synthesis in 1988. So and people started to actively use it in like around 1993. And this was the time when like Soviet system collapsed. So nobody in Soviet Union cared to teach it to students. So here in the US, like people in MIT and Stanford, they quickly put classes. And now this is taught to students everywhere. Like University of Montana, for example, their professor recently published books on FPGA for like beginners. Even in City College of San Francisco, there are classes on FPGAs. So, but in Russia, it's interesting that somebody did chat. Huh? Yeah. Okay. Yes, thank you. So in Russia, interestingly enough, they didn't have classes on FPGA in Moscow State University faculty of computing. So ВМК, вычислительная математика, кибернетика, they actually introduced it only in 2015. So, and I brought them the very first FPGA boards. Before, they didn't have it in 2015. But like MIT had this class for a long time. So you show Google for like MIT 6111. So like if you just Google for like MIT 6111. So you can find not only no, 611. So you can find not only these basic things on this basic thing on FPG. No, this is a courseware. Let's go to the real site. MIT. 1 second. Oh, no, I need to put space here. So what you see here is that students are doing some, yeah, here. So you can see here, so you can see here that students use FPGs to do work. So let's get memorable projects. Using like camera and motion, image recognition, instrumentation, audio processing. So they like so when you need to process like information like video, audio, something, when you do many parallel things at once, FPGAs, which can handle many things in parallel rather than processor, is a useful application. And you can see how different students in MIT go to, let's get something like gesture like gesture control draw. So yeah, some like a robot which is controlled by gesture. Yeah, so see, they created the whole thing, and they put here Verilog code. Yeah, so you can see here a C code which runs software, and you can see Verilog code together. So this is, yeah, so this is Verilog code. So they create here a combination of software and hardware, and they put some things in hardware and some things in FPGA, something in software and something into FPGA hardware. Okay, so yeah, and like MIT was doing this for a long time, like Stanford, like other schools. So yeah, and like so in Soviet Union, when I went in 2011 to Moscow Institute of Physics and Technology, I looked to like one of their material, and they found that they teaching like AND OR gates and D flip-flops, and then nothing, and then like microcontroller programming. So they were missing all this like RTL level completely. And this was actually taught in Moscow Institute of Electronic Technology in Zelenograd, and also in St. Petersburg, it more, but like everywhere else, there was this gap. And same thing was in Ukraine, and in places like of Kazakhstan, it's even worse. But now they used this textbook to like liquidate this most basic gap. But then I found that actually US universities have similar gaps. For instance, many students they can write like in Verilog finite state machines, but when I ask them to do some flow control tasks, like the tasks I printed, they frequently cannot do this. So once one person from a very top school, he was like rewriting his code like 10 times during a daftar interview because he was not able to figure out how to process transactions back to back with each clock cycle, or he couldn't transaction when two transactions like come at the same time in different buses and stuff like this. So I wanted him to perfectly figure it out and verify everything he is doing. And also they don't learn verification much. So student needs to verify what he is doing. And for this thing, he needs to also know some verification methodologies. And this is a part of examples which actually included into this materials. Yeah, I can go into more details in this if somebody wants, but I want to go to practical exercise. So this is like one of examples. You can use EDA Playground. Yeah, so now, once I started creating this class, so how it is used? Now we have meetings every week in Mountain View, and during these meetings, different people come. So some of them are like a recent graduate, like recent graduate from like UCLA came recent. Yes, and my son was just accepted in the UCLA yesterday, so like I was there yesterday. And some people from Google, Apple, like other companies who work in different specializations, but they're curious in this field. So there are people who work on like Google infrastructure or like Apple post-silicon debug, and they just come to get familiar with the Verilog to get like hand-on exercises. So because you see in schools, unfortunately, students are too busy with like other topics, and they don't practice with exercises enough. And if they would practice, they would have much better time during interviews. So if student go to like MIT through that class and does project, he will do well because he will learn a lot of things. But most students unfortunately don't, because they just get slides and some simple exercise from textbooks, and don't try to do something practical, working on the board. Now, yeah, but we actually joined online by people from very distant places, like this a gentleman, he is in Kenya, Nairobi, and he actually wrote some of documentation for our examples. So you see, he is using this G10 10 light board. So let me show you this board. I have it actually. Second. Yeah. So this is Altera board, which is like Altera used by many professors in school. So Philip is using this board. So it's like alternative to Govin boards, but like long history. Yeah, and so recently I had the seminar in Azerbaijan on last February. So they are trying to set up such classes in Azerbaijan, and so same thing would happen actually in Russia, like in many other countries. So they have good like software engineers, but they have gap in the area of register transfer lever and like area of field programmable gate array. So I went and had with their students like 1 week class to improve like level of their students and teachers, because like improving level of teacher is even more important, because yeah, then also we had some like seminar in Georgia and in Kyrgyzstan. So one thing which I wanted to do to try in Kyrgyzstan, but actually it didn't work. I was checking whether we can use the same thing which was used in Belarus and in Philippines, which wanted to integrate it in the world's electronic industry. So in Philippines, they also like study only software engineering and basic physics, but not logic design engineering. So a Japanese company, like I believe it was Seiko, went there and they taught system Verilog to software engineers, who work on verification environments. So they created, they were like testing Seiko designs. And this is how they created a team in Philippines. And this is how local Philippines engineers learn system Verilog and like were integrated into whole system of design. So same thing happened in Belarus. Which is like former Republic of Soviet Union. So they have like old Soviet time foundry called the Integral, where they still like making some chips, and there are some engineers around Integral, and some group of these engineers, they actually proficient in writing mothers of flash memory. And then Korean company HK Hynix went into Belarus and acquired this team. And this team became a division of Lekofa Hynix, and they started to write mothers and verification environment for their flash memory. Yeah, so now they're actually going into some complicated time because part of this team was moved into Poland, but part team is there. So, but this is like a good example how new expertise was grown up in a place where no hardware expertise before. Yeah, now also all this is working in Russia in 23 universities. So like Russian companies, because this is kind of interesting because they had this like problem for a long time and they kind of understood it. So once this was discussed in like early 2012, 2014, 15. So once they translated these books, suddenly everybody got very much enthusiastic. And the translation of this book in Russian and then creating other materials was supported by both like US and British companies which wanted to license like in Russia IP, but also schools in Russia, their companies. So like everybody suddenly got enthusiastic about this, and now the textbook and those classes are used in many places in Russia. There is a school of synthesis of digital circuit, which is classes on Saturdays, just similar to what we have right now, but instead of just one Saturdays, they actually have like 20 something Saturdays over a year. So like every Saturday, students from this 23 universities go into a room like this, get a bunch of FPGA boards and work on those FPGA projects. Some of those FPGA projects are simple and some involve like graphics, sound, processors, then they work on microarchitecture and so on. Yeah, so yeah, and also we as a group which is in Mountain View, we are going to make presentation with FPGA boards on a Maker Faire, so which is kind of artistic event. And in the past years, people on Maker Fairs, they have like some artists. So this is like a mini that one, a Burning Man combined with like Arduino type of thing. So we are going to be on Maker Faire with exactly the same thing what you see right now. So you see, you bring a bunch of such boards there, and we are going to show it to people. So essentially now, like I'm testing with you something what I plan to do in Maker Faire. Yeah, so this is all for my presentation. So from now on, we will mostly work with the boards, and I will show you some demos with like sound, with producing sound, with a microphone, like I can play flute and recognize sound on the microphone. So now what I want to do, I want like everybody to get into some place where you boot Linux and have a board and just see how many interesting pictures you can get by changing Verilog code. So you just create some like formulas and create and now like I can show you also some demos on this FPGA board. So let me drink water. So now let's go to like more hands-on practical part. And what I want to do, I want to like especially for people who study in school, I want you to think how you can make pictures in a way I just like demonstrating by specifying some formulas and drawing some color moving images on the screen. Because you can create some computer games in this way. Yeah, so let me drink water and let's start doing this. Yeah, so I think that lecture is over, and now I will show on the screen what you should do. So basically, what we do now is that you boot from this computer, from this SSD, and then you go to VS Code. And then in a VS Code, so you start VS Code, then you open folder, and you need to open Verilog projects, basics, graphic, music. Huh? So, but before we go to graphics, let's do something more simple. Okay. So let's do something very basic. So okay, so we open this folder with the basics, graphics, music. If you go to instruction on Verilog Meetup site, you can see where you can get this repository. You can get it from a GitHub. So now I know that like modern schoolers know how to work with the GitHub. So how many of work with the GitHub? So so like everybody is a repository of many software projects, including open files, like including open teams. Verilog Meet, when we create such open project which is used in many places around the world, we use GitHub place where we store files, so we can just clone GitHub repository. I will not teach you right now unless you want to install this environment on your own computer. Yeah, if you want to store it on Macintosh, you can go to Google Yossi's headquarters. By the way, if you figure out how to do this and run much of these examples, this actually has the commercial potential, because you see, I met with the president of the company which is making glowing FPGA, and if they have demo on Macintosh, I think this will help their marketing. So actually, if you can make those examples work on Upper Macintosh, you can get something useful from them, which is great, because if they write some recommendations, this can be good for like college and so on. So if you in terms of FPGA companies, so there are two large FPGA companies. One is Xilinx and another is Altera. So, so yeah, I met Gorin president recently on an exhibition. This is recording. Okay. Yeah. So the wait a second. Was it recorded or not? It's weird. Just disconnected. Yes. Anyway, so there are two large FPGA companies. One company is called Xilinx, and another company is called Altera. And Xilinx is now bought by another company, AMD, and Altera was bought by Intel. So Altera was renamed as like Intel FPGA, but now it's like renamed back into Altera. And when Intel bought Altera, a lot of journalists actually didn't have a clue what Altera is. So if you Google for like Altera Intel acquisition, because the journalists didn't understand what FPGA is, they were like writing some like weird things like this like telecom company or something else, because they like didn't understand what this thing is. You know, how can chip be without like CPU inside, and what it is, and why is it cost like $17 billion? Like I believe it was acquired for like 15 or $17 billion. So they never heard about this, and why we are talking about like such large numbers. But for Intel wanted to actually introduce FPGA cells inside their CPUs to run software with reconfigurable logic together. So I'm not sure how well this worked, but there was some like FPGA cells. And Xilinx and Altera like shared market. So Xilinx was the highest end, and Altera was like also good enough. So they went into market for like low volume specialized devices. And there were like many smaller players, like there was the Lattice and some other companies. Lattice, at some moment, some Chinese investors wanted to buy Lattice, but like Donald Trump put ban on it because he was saying that if Chinese investors buy Lattice, this can be like national security risk. So like Lattice is still US company, but in China they grew up this new company called Gorin Semiconductor, and actually I'm now a very big fan of this company because their synthesis speed is order of magnitude faster than Xilinx. With Xilinx, when you run our examples, I can show you examples with Xilinx. This can run for minutes. And if you have large design, you need to wait for like 20 minutes or half an hour, while with Gorin, it's all done in like seconds. So for like educational reasons, it makes big difference. So Altera synthesis is a little bit faster than Xilinx, but still not as much as Gorin. And also Gorin has this open source package, which is also available on a Macintosh. So, and this package this is packaged in US's headquarters. So, second, US's headquarters going. Yeah, US's headquarters GitHub. Yeah. So if you go to this US's headquarters GitHub, and if you go to releases, oh yeah, this is US's headquarters. So you need to go, yeah, to OSS CAD suite. Yeah, so this has assets. So this has x86, yeah, Darwin. So this has Darwin ARM. So I believe this is for Macintosh, right? So Darwin is a Macintosh, right? Yeah. Anyway, so if their stuff works on Macintosh, if you can make example work on Macintosh, I can send it straight to their president, because this can be beneficial for their marketing, because I didn't see that anybody runs it on Macintosh. Such examples, and this would be nice to have such a demo which can be shown on like Maker Faire. And how to use this in here. So first of all, I will show how to use regular examples, but all you have to do to run that thing is that you need to install that software and then run script called change FPGA board. So you do so if you use Linux, you can use /06. First, you need to do cd labs. So let's actually start with okay. Git branch. Oh, this is on main branch. Okay, git switch new graphics. Okay. Oh, wait a second. Did I open the right thing? Ah, yes, I think it's the right thing. Okay. Okay. So, yeah, sure. Yeah, because I did. Yeah, okay. So now, it's not clean everything. Yeah. So now you go labs, you go one basic. So let's start actually from a basic things. So first we start from a very simple exercise called AND or NOT XOR De Morgan. So De Morgan is the logic rules. It's rule of Boolean arithmetic. So how many of you know like Boolean arithmetic, like AND or like all this stuff? Yeah. So like basically, if you write like A and B, so A B is equal 1 only when both of them are equivalent. So 0 0 gives 0, 0 1 gives 0, 1 0 gives 0, and 1 1 gives 1. So this is AND. Then you have OR operation, like A or B is equal 1 if any of them is equal 1. So you have 0 0 gives 0, 0 1 gives 1, 1 0 gives 1, and 1 1 gives 1. So now what happens if you apply operation NOT? And the NOT operation is operation which converts 0 into 1 and 1 into 0. So De Morgan law is the law of Boolean arithmetic, which simply says that NOT A and B is equal NOT A or NOT B. So when you apply NOT, you need like everything inside all ends convert into OR and put not before like argument A and argument B. So this is just basic Boolean arithmetic. This is where like logic design course starts. So with this lab, you can practically see how it works. So if you go to this first example, so in this first example, let's go to first basics. Let's go here. This laptop. So here we have input. We have input called key, which is a bit vector which is connected to the keys. And then we write that we create a wire A which is connected to key 0. So key 0. So key 0 is the leftmost key. It's a key 0. And now second key is a key 1. We connected to wire called wire B. And then we compute result. As a result is equal A XOR B. This is exclusive or, but let's put AND, for instance. And then we put aside LED 0 equal result, which means that we put a result of this formula to LED, to the light. So now if we run synthesis by running script 03. Yeah, but first we need to choose appropriate FPGA board, because this board is different from board you have. This board is called Tank Primer Tank Mega one. Yeah, so this is board number 39. 39. Yeah. So now if you run a synthesis, so you can and you can run it on your board. So once it's synthesized, so you can press on button. So when you press button, you give it 1, and when you not press, you give it 0. So just a second. For some reason signing longer. So and it will show on LED the result. Yeah. Okay. Oh, and then I will show you how this code becomes schematics. But let me show you this demo first. Yeah, okay. So now it downloads configuration into FPGA. Yeah, this board is doing it slow. It's like a heavy board. Okay, so now what you do, you get these buttons and you press 1, and you press 1, and you can see that first light is dark, but second light is 1 because second light is connected to wire, which is exclusive OR. In order to make a light for the first one, you press both button 0 and button 1. So you essentially can press here button and you can see how Boolean arithmetic works. So this is your like first exercise, which is done by logic design people. So they just connect the buttons to like LED, and here is like LED number 1 is key 0 exclusive OR key 1. So exclusive OR is an operation. So what is exclusive OR? Exclusive OR is that if you if like A is equal 0 and B is equal 1, then you are getting, no, if A is equal 0, B is equal 0, you are getting 0. If A is equal 1, B is equal 0, you get 1. And here is 0 and 1, you also get 1, and 1 and 1, you call 0. So basically, you're getting 0 if A and B are the same, and you're getting 1 if they're not the same. This is what is exclusive OR. And you can implement like a circuit which does addition using exclusive OR operation. So this is something like Boolean algebra. It's something which logic design engineers start first. So you can try this demo. Then let me actually show how schematics will look like. So if you change the board to, let's say, D10 light, 14, so board number 14. So let's use a different tool chain for this board. I'm using this tool chain because it simply makes a nice visually schematics. Okay, so now you see that your code becomes a graph of logic elements. Just a moment, that you're finishing. You run it again. Yeah, then I will show you how we use board to like recognize music. So we can recognize music from a microphone. Okay, okay. So now I will run a script called. Yeah, so if you connect this to a computer, so let me connect and I will show you how this board works. Yeah, so this board. So now we can run script called 04 to configure it. Just a second, maybe it needs a different USB port. One second. It's just USB port. Yeah, some of those boards are kind of finicky. Okay, so it's buttons here and give the same behavior. So you see, you need to press both buttons to make this light on. So you press one, just with one button, only second light works, but in order to make first light work, you press both. So you both lights work. And now the good thing about using Altera boards is they have nice viewer. So script run GUI. Yeah, 05. And now I will show you what your code becomes. Okay. Okay, that's fine. Okay, so here we need actually, this is a GUI which many students who start using Altera use. So usually like professional people use scripts, but for many beginners they use such an integrated environment. The good thing of integrated environment, so we don't use integrated environment for these examples because you need to switch to many boards, and all FPGA vendors use different GUI. But anyway, here then I want you to see it is that this shows what your code became. So you can go to netlist viewers, you can go to RTL viewer, and if you click to the top module, and this is module which we are changing, you can see that your code became in AND gate and exclusive OR gate. So key 0 and 1 goes to AND gate. So this is the schematic sign for the AND operation. And like another is a schematic sign for exclusive OR operation. Yeah, and then you can see how the things are mapped into cells of FPGA. So you can like click here. So where is the top module? So they are now mapped into cells of FPGA, and then you can click to like chip planner and see how this is how this becomes some configuration on this FPGA matrix. So, but usually I show this everybody on the first session because I want to show how this code looks as a schematics. But in like real life, FPGA designers rarely do this. Mostly they're running scripts and then look reports about efficiency of something from text reports. So now let's see a couple more demos. So let me show you a demo with the music, because this is like cool demo. And actually I have flute with me. I can play flute and you can see how it recognizes flute music. So we are going to stream music. Yeah, in terms of graphics, yeah, let me show you music first. CD music. So let's go to note recognizer. Let's choose another FPGA board 06. So let's choose back this 138K Pro 39. Then run synthesis. You can actually calibrate using flute produces like sinus wave, which is very clean. So it's encroaching. But you can actually even sync to this microphone. It can listen to singing and show you the note. Yes, Oksana, can you help me to handle this thing? Oh, I need to insert it here. No, I just want you to put this little bit up, put this thing up so that everybody can see it. Yeah, okay. So now I need to configure it again. 04. Okay. All right. So now it will configure. And now like, I will show you how it works. Because usually sound processing is something complicated. It requires DSP measurement. you see, it recognizes my singing. You see, so I give see G A. You see, it recognizes notes. So now let me explain you how this works. Because the beauty part of it, this is something which school children need to understand. I mean, can actually understand. Yeah, because you see, how many of you know about the fast Fourier transform? So probably school children don't know it because it requires higher mathematics and stuff. However, everybody of you know about like sinus and cosine, right? So now, so how we recognize this music? So let's get some theory about music. So let's get so basically sound is a wave, right? This doesn't
Marker.
Yeah, yes, I need a good marker. Yeah, there was a black marker which was good, but I put it yeah, there was a black marker, but I put it somewhere. Marker, yes. Okay, so now how to recognize sound? So basically, sound is a wave, okay? But this is kind of ideal sound. Usually, when we play music, this is not exactly like sinus wave. So this is like sinus t multiplied by something. But usually, when we play music, like even flute music, it's not like perfect, but there are some like overtones here. But if you play like guitar, then you don't have a simple wave; you have a combination of multiple waves. And when you play like accords, you need to convert the sound into multiple such sinus wave, which is not what we do. But for flute, works great. So basically, that microphone, it gives us a current level, which is a sine number. So this is a 0, and some number comes positive, and some number comes negative. So basically, from microphone, you get just sequence of sounds like 10, 9, 8, 6, 3, -1, 2, 11. So we get such numbers. Now, the moment it crosses 0, here, we can detect this in FPGA. Because what we have in FPGA, we have 50 megahertz clock. And the sound frequency is 100 of hertz. So this is like music notes is like 200 something, 300 something like this. So it's this kind of
440.
Huh?
448.
Yeah. So 400, yeah, 448. So how many of you play music instruments? Yeah, great. So like basically, all you have to do to detect sound is that when you detect in your logic answer every clock cycle, that in previous clock cycle you had negative wave, and in current clock cycle you have positive. So if you found such event, you start counting. Then you have this 50 megahertz clock, and you then start count how many clock passed before it crosses 0 again. So now, once you have this number, and this number is based on 50 megahertz clock, so 50 megahertz clock divided by, like, let's say, like 500 is 100,000 clock cycles, right? So you need to create a counter which can keep number up to 100,000. So you create this like how many bit counter. So 1,000 you need 10 bit counter. So for 100 you need 6. Yeah. So you need to create a 16 bit counter, and then once it crosses this, you start counting, and you have here number. Then you use so-called lookup table, and you find, like this occur between like 430 and 450. So this must be it. So this is basically how it works. So now let me show you this. This is the code. So if you go to the code, let's actually look to this code on GitHub, because it will be just more visible on the screen. Yes, this is music. Let's go to branch new graphics. So let's go to labs. Let's go to music, note recognizer. I will make this larger so that everybody can see. Okay, so now let's make this larger. Wait. Okay, so now like everybody can see, right? Yeah. So here is the code which is actually detects this. So first we create a variable previous microphone, counter, and distance, and then we have a Verilog constant called always at postage clock or postage distance. This means that always, every time our clock signal goes from 0 to 1, every time we are doing some action. Okay. Now, when it goes from 0 to 1, we check if we have reset signal. But if we don't have reset signal, then we check that if previous left bit of microphone value was 1, which means that if number is negative, so numbers in a binary encoded as a series of bytes, a series of bits, and if bit on the left is 1, it means that number is negative. This is called the two complement system. This is also something which people learn in logic design early. So if number is negative and on previous clock cycle was negative and on current is positive, then we put our counter into distance variable and put counter to 0. So we start to count. Otherwise, we just add 1 to the counter. Okay. So essentially, this code means that if at some moment you saw that number in previous clock cycle was negative and current became positive, then we put counter 0, which means we start counting. Otherwise, we continue. Then we have a table of standard frequencies from Wikipedia. So frequency of A, as like gentleman said, is 440, but we here multiplied by 100 to use a integer arithmetic without like floating point. And then we just put some code which checks distances, and we check that our measured distance in clock cycles, so number of clock cycles between crossing 0, fits within a range. So once we figure it out that it fits within a range, we filter this a little bit. So there is some code which actually works against the case where we have noise here crossing multiple times. So we need to make sure that we somehow get rid of this noise, and then and then we finally put it on a 7-segment display. So does anybody know from you how 7-segment display works? So this one, this is not relevant, but yeah. So this is how we recognize music. Yeah, that's it. This is like a relatively small code, and so usually if people are talking about music recognition, so when you use something like Shazam or like other software, it uses some complicated mathematics called fast Fourier transform and some like other mathematics, but this is like complicated, but this is some like simple method how to recognize. Now we can in the same way synthesize music by using another peripheral here. So we have another demo how to synthesize music. So we're going to 3. So you can of course do this in a software as well, but the reason we are doing this with FPGA because such exercises are good to train design engineers because they can see some immediate effect. Then when they do a lot of exercise, they know how to like design like processors and some like 3D graphics engine or like artificial intelligence like hardware accelerators. Okay, so now it will make sound. Yeah, with this type of earbuds, it's better not to put it into ears because this is kind of loud. You see, this is like C. So C, D, so C, D, E, F, okay. So this is kind of music organ. Now the most fun part is about graphics. So with the graphics, so with the graphics to graphics. Yeah, so with the graphics, if you go to the simplest thing, color stripes. So let's go to color stripes because this is the most simple thing. So what, how does graphics works? 1 second. Stop share screen. Share, okay. Yeah, so color stripes. So I don't really want to explain you right now how a video controller works, or maybe just some like basic ideas, because you are not familiar with sequential logic yet. But like, basically, LCD graphics controller is a block in Verilog which generates signals. Where is this nice background? Just handle. Nice one, but already somewhere.
Let's just, oh, here.
Ah. Okay, so basically, this controller generates signals which go to display, right? And so this signal generates like it tells display what to draw, but we are trying not to deal with such signals. For us, it's important that this controller gives us coordinates x and y, saying that here is your x and here is your y. Give us color of this point. And basically, we look and create a formula that, like, if x is less than like 100, then red is equal like all 1. So this set is a big number which consists of all 1, so maximum number. And if you do this, we are going to see on the screen a red strip. So if you look to this code, this is what we are doing. Oh, I need to connect here this way. Sorry. But you can try it on. Oh, you can try it actually on this one. So to make it just faster. So you see, you can connect this little display, and you can make some pictures on this display. So if you run this specific test, so let me run color stripes. So now I will show you what this code does, then you see it on the screen. So here, the code is that we use combinational logic, always combat. We initially put red, green, and blue to be 0, and then we put that if x is less than 128, in this case we put color is equal to coordinate, which means that if our x is 0, it will put red color 0, and if it's 1, it put red color 1, so it will increase redness. Okay, up to 100. Yeah. So you can see that if you put such code, this is what it's going to produce. So you see, it produces strips of red, yellow, blue, and so on. So now, this is a generally basic principle of how all computer graphics works, even with a very complicated, actually, let me show you actual test we are running for GPU on emulator, on FPGA-based emulator. This is kind of remarkable because this is how we test GPUs in phones. So this is actually a test called Aztec High. No, Wildlife, yeah, Wildlife. And so this is YouTube. So let's go to Wildlife benchmark. Yeah, this one. So this is some like picture. They tell you what this picture look for Verilog designer. So you see, it's a 3D graphics. You see, such like animals. Wait, it's not everything. Wait a second, this is not complete thing. Let's see something, another one. Yeah, wildlife benchmark, 3D wildlife benchmark, wildlife extreme. Yeah, wildlife video. No, wildlife GPU. Yeah, it's okay. Let's see this. So you see, this is some like yeah, yeah, this is a good example. Yeah, you see, so it shows some scene which created completely by computer graphics with some like weird animals, like this part, with some like weird animals running. Yeah, see, it's like yeah, you see some monsters are coming from here, trying to catch us. So now, how all this look for Verilog design? So basically all this scene consists like every frame, so like every picture consists of like a very large number. So we are talking about like 100,000 range or more of triangles, of a 3D triangle. I put it again. So like basically, when you have some like monster, you get some like monster, right? And you divide all this like monster skin into like bunch of triangles. And for each triangles, in this triangle, you have some like colors. So you have like RGB here, RGB here, RGB here. So you have color and coordinates. And initially, those coordinates are all floating point numbers. And then software driver actually gives a command to draw, put coordinates of this triangles into memory and their colors, and just gives you a command to like draw it, and then you send it to processor elements like shaders, and then it goes to like my block, which is fixed function block, and in this block initially their coordinates are in a 3D space, but I need to recompute coordinates to put it into perspective and also see what fits into what we see and what doesn't fit. So we just gets this as a stream of data, and like on each clock cycle, we get this as a floating point numbers. We compute using some custom computing units. So yeah, but this all happen. This all happen in parallel with like a lot of with a lot of with like large number of data. And if you don't do it using the custom hardware, because the software, then like everything will be slow. And we are using a FPGA emulator to be able to run it before we send the mask for a chip to the silicon foundry. Yeah, so this is like basically how it connects with graphics and computer games. Yeah, now with this design, like people who actually practice with the Verilog for some small time, like a couple of weeks, if they do this intensively, they can write some simple games. So I put here a simple game example. So game with some like target, torpedo, and you can actually play this game. This game without CPU, so everything happen in a reconfigurable hardware. So so this game on FPGA which I have, it's implemented in a similar way as games implemented in like early 70s. At that moment, there were no like first microcontrollers on the market appear around like 1974. So 1970 is the first microprocessor Intel 4004, which was like those like counter machines and like supermarkets and calculators. But then processors for game machines appear more like in like late 70s. But before this, what they were doing is they just they just had bunch of like chips of small scale integration. Like one chip has like 4 AND elements, and another chip has like 4 OR elements, and another chip has like 2 D flip-flops. So they were just connecting a bunch of chips with OR and D flip-flops. And this is actually a nice way to learn basics of digital design for school children. And I like actually tried this, and even people in like kindergarten can actually understand the binary Boolean logic, like those and ORs. But to like understand sequential logic, it should be more like your age. And you can build some like finite state machines using the same logic, but to build something significant, you need to connect many elements. And they found that for high schoolers, it's kind of boring, so they get bored after like 3 days. And after this, I always move them to using FPGA, because with FPGA boards, you can do everything up to like professional level, and create your simple CPUs and so on. Okay, so now what I want to do is that we have like 40 minutes left. So I want first of all everybody to try to work with FPGA board. So I have like 2 more extra computers, and you can like practice with like any of this. So I have this computer, 1 more computer, this computer, this computer. And second, if somebody wants, I can show you how CPU, how you can build a super processor. So does anybody So how many of you know like assembly language and all this kind of stuff? Yeah, so probably if I explain the CPU, like how processor works, this will be too much information. Yeah, so now I think it's a time to just play with the PGA boards and you can just try to draw some pictures, right? So now you can ask questions.
So the demos that you showed, how does the gate level interface looks for that, and can we look at that?
Ah, yes, sure. So you want a game example, right?
Yeah, I mean even the color one was fine.
Yeah, I want to show not least not on Govin but on Altera, because on Altera it looks a little bit better. Plus there is some problem with the Govin script. So let me show you not least for Altera. So you want a color stripes, so you want game.
This is good color stripes.
Okay. So now let's switch board. So you put like D10 light, which is 14. Oh, and let's actually connect this D10 light to a display just to show that. Okay, so now let's synthesize for Altera. Then you get a little monitor to connect D10 light. For this one, this monitor. And
And also the graphics controller that you have built on the board, correct?
Actually, no, it is not. We actually implementing graphics controller in Verilog. I can show you the code. Yeah, this code is actually very simple because all you need to do is that you need to imitate H-sync and V-sync signals which originally appeared in like even black and white TVs like eternity ago. So basically you just get two counters and you just imitate this VSync and the sync signal. So all you design is two counters. That's it. Oh wait, I don't need this one. Just need to connect. But actually this is better demo. I can show it. All right. Yeah. So you can see strips here, and you can play this game here. So now let's see how schematics for this game look like. This GUI has some little bug. Okay, so first of all, we need to resynthesize it. So, okay, yeah, yes. But this is similar to me about what you those questions.
Yeah,
Because
sure.
I need some
Yeah.
feedback.
Already do some feedback by the
Ah, okay.
Yeah,
good.
sure.
See. Mhm. Yeah. Okay, so now, um, no, this is at least viewer. Okay, so now, yeah, so you can see. So this is the logic it generates for color strips. So if you see for color strips, it generates comparators and maxes. So max is a hardware. So this is like choosing. This was a comparate is a so comparator is a like listen. So if we zoom in, you can see that it generates like a less than, so b is this constant 280, and so this just like makes a multiplexer some comparator. So this is kind of circuit it generates. Yeah, now if you go back, you can see how controller looks like. So if you go back to the top, second. Yeah. So now if you go back to the top, you can see that some like additional modules. So this uses some, and let's see how controller looks inside. Yeah. Controller. Yeah. So here's a controller inside. So you can see that this circuit is not that complicated. So it has some flops which, so here different flops which is a counter for the position, and a register for vsync, hsync. Okay, so this has like circuit which like just compares conceptually HDL code for this thing. So if you go here, so this is our top. Like in our top, we instantiate the user top, which is laptop, and we instantiate VGA controller. So if you go to VGA controller, yeah, so you can see that this is like all the code. So basically, it has some combination for like accounting up to maximum, then like clock enable counter, and then it puts signal hsync and vsync when position is between certain. That's it.
So that way is like has only 3 inputs.
This display has hsync, vsync. So like hsync just tells where you on this display horizontally, vsync vertically, and it also has like inputs for red, green, and blue colors. And on this display, you have 4-bit red, 4-bit green, 4-bit blue. So you have colors from 0 to 15. You have 16. You have like 16 shades of red, green, blue. But on this LCD, you have 32-bit, 32 shades of that one, of red, 64 green, and 32 blue. But if you use HDMI, oh, this is actually beautiful thing. If you use HDMI interface, we can have 256 shades. This looks usually more interesting. Yeah, but I need to connect HDMI to that one. So I can actually do it. Yes, anyway, let's do just you can show some nice colored picture. Yeah, okay. So, like any other things? So,
So and also the welcome code that you have written Do you write the test benches as well for that? Because what if there's a mistake? And
Yes. I do have a test bench for some. So for many tests, this like test bench is very like rudimentary. So if you go to here, there is a test bench, but some of those test benches are actually complicated. This is a good question because I can show you how test bench with the verification against model. So just a moment. I need to stop the share. Okay. Okay, so if you look into this test bench, you can see that this test bench simply instantiates a laptop and runs. Yeah, this like test bench actually doesn't do anything. Let's get some more interesting test bench. Yeah, this with the color, it was not mine code. Okay, so this one also doesn't have anything. Yeah, so when we have a test bench for microarchitectural topics, for example, test bench which verify like interview questions. So this is something what they use to like automatically verify students things. So this test bench verifies this like adder with a control flow. So here I instantiate logic for the adder inputs like valid ready. Then I instantiate module which is a solution device under test. Then I run clock. So let me make it larger. Yeah. So then I run clock. Then I check for like a timeout. So if it gets stuck after like 10,000 clock cycles, I do timeout. Then I'm logging transactions. So I'm checking what is on the bus. Then I also have queues, so system Verilog queues. And every time I get a valid and a ready, I push data into this queue. So I'm modeling behavior using queues. And then like every time I'm getting result ready, I'm checking what was in the queues. And if result occur, which is unexpected, then it's like unexpected result. And otherwise, I check that I got from this adder what is some of things I popped from the from a queue. Then the simulation, I check that both my queues are empty. And I also do performance counter. So I count how many transactions are processed by clock cycles. So like in this case, I catch mistakes in like students' answers when they cannot process transactions back to back, or when they don't process different orders, that A comes before B or B comes before A. And yeah, finally I put number of transfers. Yeah. And here is the actual test. So in this actual test, first I put A and B zeros, and I run transactions back to back. So I check that it can. Then I put only A and not put B. So this is direct test. Then I put only B. Then I apply back pressure. So I check whether design can handle back pressure, and then I do a randomized test. So basically this thing automatic checks the student design, and also here I drive like random data. So every time I have valid and ready, I change this random. So this test bench actually has all features of test bench with a small number of lines. So you don't need to do all the courses, UVM, object-orientedness, and those stuff, because and the students can actually understand this conceptually on early introductory course, because you see, usually, like most of professors actually do not teach to this level. They usually just put a direct test bench that you just force signals and then look to the waveform. And in my opinion, this is not enough. So you do need to teach them like self-checking using those cues. But at the same time, like other people go too far, so they start to teach students object-oriented framework with the UVM, and then students like spend time and say, why do you need this stuff? It's just too much, you know, to do some simple things. And I think that this type of test bench goes in the middle, so it's not primitive, but not too much complicated. So they can read this 300 lines of code and understand what is going on and get idea. And if they want to build some like million line of code environments, they take classes from like Cliff Cummings or read the book and build it. Yeah.
And also, you build the same program that the color strips on two different development boards.
Yeah.
So in that case, your FPGAs are different. So
they're completely different. Yeah.
So your placement, when the placement happens, it will completely look different, right?
It will look completely different. It will look different tool chain. Basically, what they do is that I have a bunch of bash scripts, and those scripts just get number of FPGA boards you choose, and then they find out what tool chain you have to use, and then they do appropriate tool. So actually, this is like one of important part of this environment, because you see those like Xilinx and Altera people, they want professors to get stuck with their boards and not to switch to somebody else. So they give only examples which are board specific. But with this environment, professors can use one board one day, and then if they want to switch, they can use another board another day. And when I went to like Azerbaijan, I actually did experiment, was running it on like 10 different boards, and this still worked. See, and some people say, oh, this is like impossible to do. And one of things that like you see, this like Govin, like this board costs like just $120, but actually the thing is board which costs $350 from Xilinx. And even boards from Altera for like $700. So this is like several times cheaper. And this whole set here costs like less than $40. But you have to solder it. So, but if you add soldering, it's kind of $50 thing. But to do same thing with like this one, you have to spend like $200, and with so that one is much more like in a lot of people. Plus, it sounds fun, but professors are using old boards, and some of them are using boards that in like 2006 or something. Yeah, and the reason actually we created this environment, because we found that in different places in the world, people use other different boards. I can actually even show you that even if you talk about the countries of former Soviet Union, like in Minsk, they're using like Nexus 4 board, which they accidentally bought many years ago, and that board was on the market only for half a year, because after half a year, so like short time, because then Digital put Nexus DDR and said the previous one is obsolete. So, but they don't want to buy new one because this is expensive. So, but with this environment, they can still use old boards. One of like funny thing happened. Yeah, so like in all cities, like Nizhny Novgorod, Samara, like everywhere, like Baku, Azerbaijan, they all use different boards. And in Baku, they made mistakes. They bought a board without that one a programming adapter, and they just didn't know what to connect, but if you don't connect it, it doesn't work. So this was just sitting in their closet for years. And then I came and asked, wait a second, did you buy an adapter? I said, adapter? I said, okay, I have some extra. And suddenly I found that those boards in their closet all work, you know? So this is useful. Yeah, but how the scripts look like? So there are scripts written in Bash scripting language. For each tool chain, it shows some set of functions. Like you see, for Goin, you how to set up, how to run synthesis, and so this is all like automatic. And you just have one push button sync, and you can use many different FPGAs. Okay, so like any other questions? General like what happened in like electronic companies and like anything you curious about?
How about the GDS file?
Huh?
GDS file.
Yeah, GDS is only for ASICs. So but I do have scripts which generate GDS. And this is actually a good question because I can show you how it is run. I can show ASIC synthesis for a CPU. Unfortunately, it runs for a long time. But let me see if I have it already run here. So visualize ASIC. So if you go to, let me just show you screenshots. Okay. I think yes, I have a screenshots here. So I have screenshots. So when we run ASIC, so when we run ASIC design tools, so let's get CPU. Yeah, this is a school RISC-V CPU. This was created by a person, Stanislav Zhevnyev, who was a Java programmer, but he started to make such exercises. Now he is processor designer. So he works in a company called Syntacor, which make RISC-V cores. And yeah, and he wrote this specifically for school children. And here I synthesize it for ASIC. So this is a simulator for RISC-V instructions, and this is screenshot for simulator at work. Okay, and this one is like another. Yeah, let's go to the end here. Yeah, so this is how GDS2 file looks in a K layout viewer after you run ASIC synthesis using OpenLane, and after you run like place and route. So this is like such screenshot, and this is how it looks with like different scales. So you can see what the processor occupies on a die, and so here. No, this is Altera screenshot. Yeah, so those are screenshots, then like it produces reports of how much is occupied and how it fits into clock cycle budget. But you see, one thing is that with this thing, like everybody can like experience this for free and create like their own chip using a tiny tape out. The only problem with it, you cannot create chips with like 3 nanometer thing, but you can create with 130 nanometer, and you cannot create something large. You can create only small. Yeah, but those tools right now, their level is similar to like Linux level in like early 90s. So like in early 90s, like Linux was a very weak and Windows was very strong, but then Linux became developed. So there is a hope that free tools for ASIC design also develop. Yeah. Okay. So like anybody else, questions, general subjects, topics about anything. Which electronic company in Silicon Valley has the best food? So yeah. Okay, so if you want, yeah, by the way, if you're curious to try it at home, like actually I can either sell or even like borrow it to you, because my son is now studying in UCLA. If you don't like it, you can return it to him. So this is like a fine idea. Or you can buy it from me for like $50 because parts cost like something like this. So if you have interest in taking part for developing such examples, you can join Zoom call over in like Mountain View, or you can get a list and get such components on AliExpress. So they're all available like on AliExpress. Also, if you want to go to Maker Faire in Vallejo, it's kind of for you a long drive from here, but if you never went there, it's fun. So have like anybody visited Maker Faire? No, I can show you how it looks like. So Maker Faire. Yeah, so they have such figures like this. You see some like sculptures which make like fire, and yeah, such like octopus and like robots and various like hobbits and some like art shows. So like we plan to put FPGA boards on a Maker Faire. Yeah. All right. So I think that. Okay, so I will in this case start to like putting everything back. If somebody want to play with this board over there, like board is over there, so you can try to run some demos.
So any behavioral questions?
Oh, excellent question. So I'm not sure I should record this. Okay. So there are when you like interview in different electronic companies, there are actually different approach to like interviewing people. Because like some companies people like in Samsung, they value like technical competency to the highest. So basically, so basically how like interview like look like. So first you send your resume like around. You can send directly to Samsung, or you can send to Post, and then like recruiter contacts you using email. Then you call, and then you discuss with like a recruiter who kind of doesn't make a lot of judgment about yourself. So he just like finds basically if you are interested in position and if you have some basic qualification for it, then let hiring manager to do you a screening interview. So then he schedules to do a screening interview, and this might be hiring manager or might be some senior engineer like me. So sometimes like my boss is coming to me and says, Yuri, can you screen this like intern or junior engineer or somebody else? I said, okay. So then like what happened is that so we now do it mostly over Zoom, but sometimes in person. So then we schedule like 1 hour of time on Zoom. And then we go to Zoom, and then first I ask like what he was doing in the past. Then like ask. Um, so usually to ask to like explain, to see how he like explains the structure of his blog. You know, then after this, I start to give him like puzzles, similar to like puzzles I show. So a puzzle like here is a block, right block in Verilog, which like converts like wide data bus into narrow data bus, or which like has some flow control. But different engineers have different favorite questions. So some people ask like finite state machines, some ask like arbiters. In like networking companies love to ask reorder buffers, and like Apple asks very interesting questions, like elegant, technical, yeah. And then like basically if person doing well on such questions, then he is going to a big interview. And big interview can be in one day, and this is usually long. It's like 4 hours, so people speak with like up to 6 engineers. No, not 6. Usually like 3. Usually like up to 4. So four engineers. Engineers spend like 45 minutes. Then each of them is doing the same thing. So ask previous project, ask to solve some puzzles. Now they all together write reports to the manager, and then like we all go together to some room and discuss what everybody observed. And the different engineers ask different questions. Now after this, if we generally decide that nobody has some very negative minus against him, and people are generally positive, then he is talking with like a manager of the engineering team, who is asking him something about his like education, like background and so on. And by the way, graduating from like a top school does not guarantee like anything, because I saw people from like top expensive schools who did very poorly on like technical questions, and some people from like no-name schools who did great. Now, and a similar kind of interview is done in like many other companies, like AMD, Juniper, Apple, like Nvidia, like companies like similar. Yeah. Now, but there are some other companies, and those companies they actually ask technical questions more light. So they ask something what you can like answer after practicing. My examples very easy. So like something like that. You got some like a pulse arriving and then generate something else, use like another frequency. So something like very like nothing hard, but they put a lot of like emphasis on like behavioral questions. So ask like questions that like what if like 2 people on a team do not agree on something and you some disagree, so what to do in this case? And they also get like a bunch of managers who are not a field, who do not like designed manufacturing, and ask you, want you to write some like story about why do you like space travel or something, and then like judging this. But I personally prefer companies who judge on technical competency, because I think that if person is technically good, he is most likely to be okay to work with, because generally like smart people look alike. Yeah, but there are companies which follow different philosophy. Yeah. So how it works? Huh?
Can you name the
No, I just like we put this on like YouTube. I don't want to name names, you know. But like my personal take, I personally like companies which like value somebody who is like a technical problem solver, who can clearly explain like his design, who can like think clearly, do the job, and like the cause is like a soft saying. I mean, it's not likely that a person who is good at this thing to be like a bad human being. You know? So, okay. Yep.
На русском языке.
Да.
Сейчас в IT, я так понимаю, ну, все наверняка слышали, что сложности, например, в перечиках возникает quality assurance. И очень часто такое есть мнение у знакомых, что многие проекты, например, закрываются здесь, либо набираются работники из других стран, и все это делается на удаленках, и так далее. Как страшна такая ситуация для этой области?
Ну, я тут живу 33 года, поэтому я видел все эти процессы в разное время. Вот. Но в этой отрасли... Дело в том, что в этой отрасли аутсорс не настолько сильно распространен, как в других, потому что код для всех этих процессоров GPU, он гораздо больше контролируется. Вот. То есть тут, так сказать, утечка, поэтому компании все-таки предпочитают иметь постоянных работников, которые типа свои. Потому что, ну я же говорю, что внесение ошибки в дизайн может превратиться в 20-миллионные потери. Поэтому стараются все-таки, чтобы были свои люди, а контракторы используют только на но сильный аутсорс в Индию, в Китай делают некоторые стартапы, но то, что я видел, они при этом там имеют... То есть тут, если иметь хорошо развитую техническую компетентность, то все эти вещи они не особо страшны, поскольку сейчас имеется некоторый дефицит вот людей с компетентностью. Вот. Ну, то есть, вы, конечно, слышали про всякие там увольнения, там, там просто очень много людей, поэтому там вот. Я думаю, что в целом это несколько больше защищено, потому что тут меньше commoditification. То есть commodity, когда работа превращается в commodity. То есть commodity это типа взаимозаменяемые люди. Ну, вот люди, которые копают канавы, они там стоят фиангу, можно взять от любого. А вот в этой области этого меньше. Вот. Потому что, да, то есть для компании желательно, чтобы человек, значит, работал много лет, владел этим блоком. Вот. Ну, хотя, конечно, всякое может случиться.
И учиться нужно постоянно, да?
Ну, это же желательно. То есть есть, конечно, всякие странные случаи. То есть я вообще встретил человека, который прожил всю жизнь с типа конца 60-х до типа 2010 года тем, что он программировал на IBM 60 бухгалтерские программы. То есть в банках это еще осталось какой-то legacy код. Вот. А? Да, это уже просто человек на это просто сидел, и так как он был там кому-то нужен, то он там, значит, да, но как правило, желательно, конечно, учиться, то есть брать все время новые курсы, смотреть.
Насколько сейчас широкий запрос в этой работников?
Ну, конкретно сейчас, в сию минуту, вот, сейчас хайринг не очень ход, хотя ко мне все время приходят какие-то предложения вот этих от рекрутеров. Ну, компания, особенно учитывая нынешний пуш на AI, когда нужно для этих ускорителей искусственного интеллекта делать ту же самую верификацию, то есть это для хардвера, то, конечно, предложение сейчас не появляется очень вяло. То есть, вот, скажем, вот в нашу группу мы очень активно нанимали год назад, то сейчас это не так. То сейчас это только особый случай. Но, возможно, в следующем году будет лучше. То есть это вещи, которые ходят циклично. Вот у них был большой спад после краша доткома в 2000 году, был достаточно большой спад после 2008. Вот. Ну, сейчас это такой мелкий спад. Это пройдет. Вот. No. Окей. So, да. Да, это вот это вот, в смысле, это Харрис. Да, да, ну вот, она может ее просто сфотографировать. Вот. Ну, то есть есть книги и ну, в этой книжке, если я бы, вот если вот вы хотите это все, там есть много, грубо говоря, лишней информации, то есть я бы там много пропустил аж до главы 4. То есть вначале оно там медленно описывается, все цифровую логику, это все полезно. Некоторые вещи, типа там карт Карно, они не так особенно нужны для современной работы, но вот, скажем, вот в России, где там у молодежи сейчас повышенная мотивация, там есть куча людей, которые мне пишут, я прочел книжку от корки до корки, там, вот. Но вот я бы на вашем месте бы читал, пропуская места, которые не имеют прямого отношения. Вот те же вот карты Карно. Вот. Но если ее всю пройти хорошо, то можно понять введение сразу в несколько профессий. То есть не только в цифровую логику, но и там в тоже там программирование встроенных систем, например. Это хорошо. То есть в ней нет ничего особенного, они как бы скомпилировали несколько книжек в одну и написали все это таким вот живым языком. Okay. Хорошо, тогда я буду все сгребать. Вот. Все.